Okay, so welcome to the last lecture of the school, which I hope you have enjoyed. And this talk will be given by two lecturers as this morning, so Alberto Garcia Duran and Mathias Niepert from NEC Labs Europe, and they will talk about learning from multimodal graphs. So let's welcome the speakers.
This one also works. Okay. I have. Yes. Okay. Thank you very much for the introduction. Thanks for the invitation, and I also want to use this opportunity to thank again the organizers, Ricardo, Fabrizio. It's been really fun, and also thanks to the rest of the audience for sticking around until the last lecture. Okay, this lecture is about learning from multimodal graphs. And my lecture will specifically focus on learning in general from graphs. So for instance, knowledge graphs, but also graphs where we just have a single relation between the nodes. And then the second part taught by Alberto will actually be more about the multimodal part. Here, multimodal, just so that you already know this, is kind of, maybe having images on top of just the relational structure, maybe also text, both. Additional numerical features, these are the things that Alberto will talk about. So I think most of the previous speakers actually have a university background, and you all know, of course, how a university looks like from the inside, I assume. So before I start with my actual lecture, I wanted to also talk a bit about, the company and, what we're actually doing, because we're not just doing what I'm presenting today. So NEC, in case not everyone knows that, is a Japanese company. I always like to say it's like the General Electric or the Siemens of Japan. So they're active in many different business domains. And they also have a bunch of labs. So there are labs in the US, labs in China, and the labs in Europe happen to be in Heidelberg in Germany. We are still trying to figure out why, but that's the case. We have about 80 researchers, and about 80% of us have a PhD. We are a pure research lab. So while, of course, the type of work that we do is informed and motivated partially also by the business applications inside of the company, we are relatively free and we are not really working on products. So the goal is to actually do technology, what we call technology transfer. So we want to publish top-tier conferences. We want to build stable prototypes, implementations of what we do. We want to give this to the business units. And then also we work a bit on patents. So it's one of the things also that we do. Yes. Then also, which is maybe a bit special also about our lab, is that, of course, our research, as I mentioned, is informed by different business domains inside of the company, like digital health, retail, finance, the usual stuff. But we are also participating in projects with other universities and companies. We also fund sometimes PhD students, and we also have third-party local collaborations in the region where we are. So, for instance, the University of Heidelberg, but also the German Cancer Research Center. And this is also a way for us to, understand kind of where research is going in different areas, and to also stay connected to academia, right? Which is also really important for industrial research. The group that I'm part of is called the Systems and Machine Learning Research Group. We have about 14 machine learning researchers and 12 systems researchers. And the main research themes are multimodal, so learning from text, images, numerical features, relational features, all at the same time. Graph-based machine learning, which also includes unsupervised and semi-supervised learning. And then I mentioned before, right? We have also about half of our group is actually systems researchers, so they're working on things like TCP/IP, operating systems, networks. And so part of our work is also about how to improve systems for machine learning and how to use machine learning to debug and understand systems. But of course, this is nothing that I'm going to talk about today. In terms of the, let's say, current technological challenges, so when you now go and you talk to business units within the company and you ask, what do you need? Like, what are your problems? There's a set of reoccurring themes here that I also briefly wanted to mention to you. So for instance, machine learning that works without much labeled data. So maybe for computer vision, for object recognition, we have a lot of labeled data now, right? ImageNet and so forth. And there things are going pretty well. But in many other application domains, just to give an example, for instance, digital health, it's very expensive to label data. And so the problem of having not enough labeled data is very, very common also in industry. Then also, and I'm sure you have heard about this, interpretable and explainable AI. I mean, the verdict of what that actually is, I think, is still out there. It's oftentimes very application dependent, but it is very important. And I will also mention this later when I talk about how we are trying to combine rule-based AI, so good old-fashioned AI, with the more novel representation learning AI. Obviously, we want to combine different modalities. This is what mainly the second half of the talk is about. And we want it to be efficient in some cases at least. So since this talk is going to be about graph-based machine learning, I also wanted to motivate in a sense, so why do we actually care about graph-based machine learning, right? So why do we even work on that stuff? And what is it actually, what I mean when I say graph-based machine learning? So I think there are essentially three different ways to learn from graphs, kind of categorized according to the type of input and the problems that you're trying to solve. The first one is, given a collection of graphs, so for instance, you can imagine a bunch of molecules, let's say, that are modeled as graphs. You want to now learn a representation for those graphs that you can then use in some sort of downstream task. So you might want to classify graphs as toxic or non-toxic to certain cancer cells, let's say. Another problem is, okay, let's say you actually don't have a graph and you have very little labeled data. Then oftentimes what you want to do is you want to actually induce a graph, which is called, a type of manifold learning. And then you want to embed that graph, and then you can use it downstream for some sort of computation. So even if the graph, in a sense, is not given in the beginning, you can use graph-based machine learning actually in many application domains, especially if you have little labeled data. Another type of problem is given a huge graph, or given a huge knowledge graph, and this is what my talk is going to focus on, where we have different types of relations. We have maybe also numerical features, visual features. We want to also learn a representation from these graphs. And we want to perform something like link prediction, node classification. And I'm going to give you a couple of examples now also to make this a bit more clear. So one instance I already mentioned, it's the example, okay, let's say you have a lab and doing wet lab experiments is expensive. So you can synthesize molecules in the lab. But you first want to narrow down your search, right? And so one of the things that you can use here is this type of graph-based learning where you try to understand and try to learn representations on a collection of graphs that tells you, for instance, whether certain molecules are toxic to cancer cells. And then you can narrow down your search on the ones that the machine learning deemed important. Another area that we work on is digital health. So this is an example of, we actually don't have a graph. We have maybe just medical records of patients with a lot of missing data. So this is also something that is crucially important in practice. And we actually induce a graph between the patients in some way using some domain knowledge. And then we learn some sort of representation for that graph that we can then use, for instance, to predict in-hospital mortality. So, what is the outcome, the likely outcome of the patient, so that in this case we can then maybe allocate more resources if needed. Another one where we have applied successfully also knowledge graph embedding methods is actually recommender systems. And of course, in the context of recommender systems, actually the problem already comes as a graph. Right? We have customers as nodes, we have products as nodes. The relationships here are essentially the reviews, the scores, or the text that was written for the products. And now we want to perform link prediction, right? We want to actually find, for a given customer, which of the products might this customer be interested in. So it's a form of link prediction problem. And then another problem that we also have worked on is essentially polypharmacy. So we want to understand, given two drugs, what is the likely side effect that these two drugs will have. And I mean side effects where when you look at the drugs individually, you don't have it, right? So essentially drug-drug interactions. And you can model a lot of these protein-protein networks, also the links between drugs and what proteins are they targeting, also as a knowledge graph. And you can actually apply pretty straightforwardly knowledge graph completion methods to also answer questions here like, you know, what are the likely side effects between drugs? So just to give you kind of an idea of why is learning from graphs or graph-based machine learning actually important in practice and also for companies. Another thing that I also briefly wanted to mention, Alberto will talk about this a bit more, is now we can also think about maybe more complex queries, like visual queries, for instance, right? So that's also something we have been working on. Maybe we want to actually not just ask, given an entity and the relation, what's the most likely other entity that is linked to? We might actually maybe want to have two unseen images and ask, what's the most likely relationship between the entities that are depicted in these images, right? So these kinds of things also Alberto will talk about. Okay, so this was kind of to give you a bit of kind of the motivation and the background. You know, why is it that our lab cares about learning from graph structured data? And also maybe my talk is a bit, in that sense, a bit different because our assumption is more like, okay, we have a large data set that might already come in a relational form. It's actually very, very common in businesses that you have relational data in form of databases, right? And so what can you do with it? As opposed to starting, in a sense, with maybe the logical formalism or the SRL formalism and then trying to understand how to scale it up. I have also worked on these topics, but this is more like, let's say, more the data-driven perspective, I think, on learning from graphs. Okay, so the outline of my talk is as follows. I will actually introduce some basic concepts, and I already apologize if to many of you, this will be trivial, but I thought, you know, I want to kind of have every one of you on board when I actually talk about things like, you know, dot product between vectors, these kinds of things. So I want to get a very brief introduction into kind of, you know, representation learning 101, which you don't really, much easier than logic, right? And I think most of you have a logic background. Then I personally like to think about, you know, I think about when it comes to learning from graphs, I like to think about it as kind of being, you can approach this from two different perspectives. One is you can think of a multi-relational graph as a tensor, so a higher dimensional matrix. And then you can do stuff to actually decompose that matrix in certain ways. And then you can use that to predict links, for instance. Another perspective that I like a lot is actually you want to learn from local structures, right? So it's very difficult because graphs are very heterogeneous, right? Every graph looks different, has maybe a different number of nodes. So you need to think about what does actually locality and learning from local structures mean when we are looking at graphs, right? For images, it's obvious. We just look at a square grid and move it over the image. That's what the deep learning guys do, right? But what do we actually do for graphs where we have a highly irregular structure? And this is also something that I will address in my talk, in my lecture. And then I also wanted to conclude with some practical observations. So, you know, what is our experience? Like, you know, what works, what doesn't work in practice, what's good in research? Maybe, you know, to publish a paper is maybe not the best of what you really need in industry. So I wanted to also give you a bit of, like, some final words on that before I hand it over to Alberto. Okay, so what is actually the problem that this lecture addresses? So the core problem that you can kind of keep in the back of your head is always given some sort of multi-relational graph, what many people now call a knowledge graph. We want to learn a representation here. And the representation doesn't have to look like the one that you see here, right? Some sort of vector representation. Even though in many cases we will actually do that, but we will later also talk about how we can combine vector representations of graphs with logical representations so that you kind of keep the nice interpretability of logic AI. We are interested in learning representations that can answer us questions about properties of nodes. So for instance, what is the diagnosis of the beardy guy in this graph here? We want to predict properties of links. What's the rating that the user would likely give to a particular product? We want to talk about and predict properties about graphs. We want to predict missing links. Again, this is what I'm going to focus on specifically, and also kind of explain what the community has been doing there, and what are the evaluation measures, these kinds of things. And then also maybe more complex queries, which is kind of more like I think where people are going right now. Not just the simple like predict a link, but can you actually have, for instance, a conjunctive query, and you want to answer now and return the probability of particular substitutions for that query. Also, and before I get really started, I wanted to put this disclaimer up. I've worked actually, I'd mentioned this before, I've worked a lot with Markov logic, for instance, and these are very cool methods, and they work really well in many application domains. But my assumption here is that this is something that has been covered before. And so not mentioning this doesn't mean that I disrespect it. The hope that we have in our research group is that eventually we can combine the advantages of these both kind of, different parties here. The one which is more coming from a logic perspective, and the one that's coming more from a neural network-based perspective. And this, of course, has been mentioned before in other lectures. Okay, just very basic graph terminology. I found it always, this is what I meant earlier, but it's probably trivial. But I just wanted to make sure that when I use particular terms that you know what I'm actually talking about. And so I just wanted to make sure that you know that, we talk, when I say node identifier or node label, I mean something like the title of a node, right, the go-to museum. Node, entity, and object I will oftentimes use interchangeably. Of course, this is maybe painful for a logician, but sorry, this is kind of what I, by accident, oftentimes do anyway. So when I say any of these words, I mean just kind of a node or an object or an entity in a graph. Then there are also, depending on the literature, actually, different notions for what actually a predicate here, or like a link, right? A link type could actually be called. So in the NLP literature, it's oftentimes, or knowledge-based completion, relation type, relation sometimes also, and then also predicate. And then what Alberto is going to talk about quite a bit is, when you also have features on the nodes, like images, numerical features, these kinds of things. And when we only have a multi-relational graph, so no additional node features, then we can simply represent such a graph as a set of triples. So that's kind of the very simplifying assumption that the knowledge-based community is actually making. That also maybe already some of you might disagree with, but that's kind of my assumption here. Then when I say vector, I obviously mean a vector matrix tensor, just going from, increasing the number of dimensions that we essentially have. A summation between vectors is obvious. It's good to kind of keep in mind when you sum two vectors, it's kind of like translating the first vector, so moving the first vector by a certain, in a certain direction by the second vector. Element-wise multiplication, so there are, when you have vectors, you have two types of multiplications that are very commonly used also in the deep learning literature, is the element-wise multiplication and the vector dot product, which also has a geometric interpretation, but I'm not going to go into this right now. And then the same is also true, of course, when you look at products between matrices. I mean, element-wise multiplication is obvious what that is, very, very trivial. And then a matrix multiplication, which happens a lot, this is kind of what all of deep learning is kind of sitting on, right? Is obviously, you kind of, you can see, and you can think of this geometrically as a particular linear transformation, right? It transforms one space essentially into another. So just very quickly, then what, a lot of machine learning has also been about in the last 10, 20 years is about actually factorizing matrices, right? So you have maybe, the classical example is, if you have users and movies, let's say, you have a very sparse matrix with the ratings. You can now decompose that matrix, right, into low-rank matrices, so that the product, so the matrix product between these two matrices reconstructs, in a sense, well, the original matrix. So it's a way to approximate the original matrix with a product of low-rank matrices, and that is oftentimes very successfully used in recommender systems. And so another way to think about this is, instead of saying, okay, we have a matrix, and now we are thinking mathematically about how to decompose it and what's kind of the set of formulas, another way to look at this is to just say, okay, we assume that the users in the movies are represented with a one-hot encoding, right? A one-hot encoding is just essentially encoding every entity that you have in your graph here as an integer. Then we have an embedding function, and an embedding function, a linear embedding function, is just essentially multiplying this one-hot encoding with a matrix of parameters that you actually learn during training. So it's kind of like a lookup in a sense, right? You're looking up one of the rows in this matrix, depending on where your one sits here, right? Then you get a particular, what is sometimes called low-dimensional representation of your entities, right? In this case, movies and users. Then you define a scoring function, right? So the scoring function tells you kind of, given a user and a movie, the score is proportional to, let's say, for instance, the rating that the user might give to the movie, right? That's something that you can learn. So you define the scoring function as a dot product here. It's a very common scoring function, just the dot product. Then you define a loss. You say, okay, for the ratings that I have, right? I want that this kind of dot product here between the movie and the user is actually very close to the actual rating, right? And this difference, and then some sort of a difference between the two gives you the loss. And then you can simply apply gradient descent, and in the end, what you end up with is representations. So these low-dimensional representations for your users and your movies. Okay, the reason why I tell you this is because what people do in knowledge-based completion is actually very, very similar. It's just going essentially one dimension up. And that's because when you look at the multi-relational graph, it's very obvious that you can actually represent that as a three-dimensional tensor, right? Where x and y axis are something like identifying the pair of entities, right? So the first entity in a triple, right? I told you that a knowledge graph can always be represented as a triple if you don't have any additional features. So this particular coordinate here is essentially identifying where is this triple sitting in this tensor, okay? And of course, if you have a particular knowledge graph, then you have essentially a 1 here if this particular triple is true, and you have a 0 if it's not true, right? And so this is very reminiscent, I hope, of what I showed you earlier about recommender systems. And then the idea is very similar also to what people do in recommender systems. Now you can think about, okay, I have a three-dimensional tensor. Now how can I actually decompose this three-dimensional tensor into representations of entities, so vectors, and representations of relations. So that then at test time, I can just perform the scoring function that I mentioned before, and then see, okay, the higher the score, the more likely is it that there is actually a true triple here. And so we are mirroring essentially just what I did earlier with the recommender system problem. We choose a representation, so an encoding of entities and relations. So for entities, it can just be, a vector of a particular length. For Rescal, which was the first, I think, the first modern way of applying these kinds of ideas to knowledge-based completion, you can use a matrix. So relations in this case are represented as matrices that have on both sides essentially the same number of elements like the entities. Then you define the scoring function. Again, the scoring function is trained to be proportional to how confident you are that this is actually true, right? That the triple is actually true. So you do now this, vector matrix multiplication and then vector-vector dot product. You define a loss function, and you can train the whole thing. And then in the end, you can just compute the score for things where you don't know if they are true or not. And you can now also rank essentially triples according to that score. And that's, in a nutshell, what people in knowledge-based completion actually do. Very simple. And after this first paper, and I will also mention a paper, Alberto actually was also an author of another paper that another method that I will mention in a second. But now you have at least, I would say, about 50 papers per month coming out on this particular problem. And the only difference in many cases is kind of how do you actually combine the representations of the entities and the relations with each other to get a score. So another very, very popular embedding method or scoring function is dismult. The assumption here is that you have for entities a vector like before, but also now for a relation you have a vector. This is essentially just assuming that the matrix that we saw before here has only non-zero elements in the diagonal. It's the same thing. And then you say, okay, the score of my triple, so the likelihood that my triple is true, is proportional to the element-wise product of the two entity vectors, dot product with the relation vector. Okay? And then again, you train, using gradient descent, you backpropagate, you train your embedding, and then you can use that test time to make a prediction. A slightly different kind of approach, this is what I mentioned, Alberto is one of the co-authors of this paper, is to actually think about triples as translating, or relationships as translating the head entity, so the entity that's in the first position of a triple, to the tail entity, so the entity that's in the third position of a triple. So for instance, given a particular triple that we know to be true, we now essentially train the model so that the embedding of Tokyo here, translated, right, by the embedding of the relation capital of, should be roughly lead us to the embedding of the entity Japan, right? And now you can again train the whole thing end to end with backpropagation, and at test time, given an entity and a relation embedding, you now look at all of these other possible entities, you compute your score here, and you rank. Very simple. The geometric interpretation here is that relation vectors translate or move head entity embeddings to the tail entity embeddings. So this is actually reminiscent of what we heard earlier today, because this is also something that people do, or well, similar in word embeddings, right? Where they could show, oh, once we have trained our word embeddings, we also have this kind of this analogical reasoning, right? I don't know, prince minus or prince minus male is princess or something like this. This is what they could show. And as I said, there are many different scoring functions. And there are lots and lots of papers on this. So for instance, as I said, Rescal and Trans-E, we now understand. We understand dismult. So just a slightly different type of scoring triples. And then there are also more recent approaches, for instance, complex. This is from Sebastian Riedel's group. But they're all really only different in the way that they score, that they compute a score from the representation, so the embeddings of entities and relationships. Okay, then also, and I will mention this a bit later, this is one of the big disadvantages of, by the way, this is not deep learning, right? So this is actually neural network-based learning, but it's not deep because at the moment we're not talking about images or text or something like this. So this is actually shallow neural network-based learning. But still, one of the big disadvantages for this type of learning is that the results oftentimes depend very crucially on how you tune and what kind of hyperparameters you actually choose for your model. And the loss function is one of those very crucial hyperparameters. Of course, the loss function, as I mentioned before, combines essentially the true triples that you know in your knowledge graph with some sort of scoring function that we just talked about earlier into a loss function, right? So we know the true triples. We have currently our scoring, our machine learning model that can score triples. Now we can test how good are we actually at scoring the ones that we know to be true. Now the problem in knowledge bases is that we have or at least we should make the open world assumption, right? If we want to make link predictions, so if we want to predict new triples that are not actually in the knowledge graph, we should make the open world assumption. And this means that we only know that the triples that are in the knowledge graph are true, but we don't know triples that are false, right? We just assume that the triples that are not there, they can be true or they can be false. We just don't know it. And so what is typically done, so essentially the problem here is, how do we generate negative training data, right? If we only have positive examples. And the way that people kind of circumvent this problem is by coming up with losses where you randomly generate triples that are probably false, but we don't know. They could be false or true, right? Because we make the open world assumption. But then you actually compare a triple that you know to be true and its score with a triple that you randomly generated. And you train the model so that the triple that you know to be true gets a higher score, right, than the triple of which you don't know if it is true or false. So this is what's called usually, negative sampling. And there are two losses that are commonly used here. One is the margin-based loss, and the other one is the softmax-based loss. Margin-based essentially means we take the true triple and look at the score. We take some randomly triple by, for instance, corrupting, so randomly sample a tail entity from the knowledge graph. And we look at the difference. And so if this is very small, right, this is bad. If this is actually high, this is bad. And the same is also true for the softmax loss. So you look at this is the score of the true triple, and you are now randomly sampling a fixed number of corrupted triples. Like here we just sampled one. Here you sample a fixed number, and then you apply a particular loss function, which is called the softmax normalization, and then the cross entropy loss. So you want essentially this to be the highest, to get the highest score, right, compared to all of the negative sampled triples. So this is kind of how people kind of, as I said, circumvent the problem of not having any negative training examples. Okay, so now if you want to participate in the, you have a good idea for a new scoring function, or maybe even something completely new, and now you want to see, does it actually work? So what do people do there? There are a couple of benchmark data sets. FB here stands for Freebase, and this stands for WordNet. These are two knowledge graphs. I mean, I'm sure most of you have heard about them, and there are many others, right? DBpedia and so forth, Iago. But these are the ones that are usually used. What you do is you split up the knowledge graph into a fixed split of training data, validation data to tune the hyperparameters, and test data. And then what you do is you look at all of the test triples one at a time. You substitute the tail entity with all of the possible entities in your knowledge graph. You apply your trained model to score, right? And then you apply a ranking-based measure. So in the end, what we do here is, because we are looking at absolute scores, what we usually do is we kind of rank the triples and then apply scores that you also typically find, for instance, in information retrieval. Also, what is usually done, because sometimes you have a particular test triple, but there is another triple that's actually also true for a certain substitution of the tail entity. So what you do is you just remove those, so that you remove at first all of the ones that are correct, and then you compute the rank, so the position in this ranked list of the true triple that your scoring function determined. And then if you want to compute a typical evaluation measure is hits at 10, is essentially answering the question, is the correct entity among the top X ranked entities, right? And then you get the score. And this is what people usually use. Or you can compute the mean rank, so you get the ranks for all of the test triples, you just average it. Or you compute what's called the mean reciprocal rank. It's essentially the same thing. You compute the ranks for all the test triples, and then you compute the sum of one over the rank, right? This is a bit less susceptible to outliers. So if you take the mean of all of the ranks, and you have one rank that's really, really terrible, like 10,000 or whatever, then it skews essentially the mean very much to that particular one outlier, whereas this measure here is much more robust to outliers. So that's why oftentimes people use both, or should use both. Right. And then, yeah, so I mentioned there are lots and lots of methods. As I said, many of these methods actually just are different in terms of their scoring function. And this is kind of a typical, I would say, it describes pretty well what's happening in representation learning nowadays, is that you get hundreds of papers where the one paper that's new is by 0.5 percentage points better than the previous one. And then after a while, there is one paper that actually shows, well, if you only tune the simple model better, it actually outperforms all the previous ones. right? And so this is actually what's more or less happening in this area. So you have lots of, very, very interesting, I mean, I'm not, against that type of research. It's just that oftentimes when you tune the model correctly, like in this case here, Dismold, you can actually show that you're pretty competitive. You usually outperform the other methods. And so, as I said before, it depends a lot on your hyperparameter choices, like the loss, how many negative triples do you sample for the loss, what's your learning rate, these kinds of things. And so it's very, very difficult now, I think, to really improve this, I think, because we are also, with the benchmark data sets, really kind of, we reached a ceiling. And so that's why I think also the right way to go now is if someone is interested in this type of work, is to go beyond these very simple scoring functions that I just showed you, and to try more complex ideas. Like, for instance, how do we actually combine rules that you can also mine or that you can have as background knowledge in these knowledge graphs? How do you incorporate that in the learning process? Or how do you incorporate text data if it's sitting on the nodes, and these kinds of things? So that's, I think, where lots of people are moving right now. And if you're interested kind of in the background on this particular topic of these kind of, let's put them as, simple scoring functions for knowledge-based completion, there is also a nice review from Maximilian Nickel. Again, Maximilian Nickel kind of also, I would say, really jump-started this whole area. And I think for those of you who stay on for ILP, he's also one of the invited speakers there. And then also, recent developments, which are also, I would say, are going a bit kind of beyond just kind of thinking about these very, very simple scoring functions, is to actually think about, okay, can we actually embed also knowledge graphs into spaces that are not Euclidean, right? So for instance, this is an embedding into a hyperbolic space. And what's, for instance, what you can very nicely do here is if you have a knowledge graph that's hierarchical, right? Something like an ontology or like a very hierarchical ontology. Then these new types of methods are extremely good at embedding these things into even just a two-dimensional space. So I think this is a recent development that's quite interesting, and that also maybe gets us a bit away from, okay, what's the next scoring function that improves the state of the art by 0.5%? So as I said, my background is also a lot on Markov logic, statistical rational learning, using also rule-based systems. So one of the things, after also working with Alberto on this topic a lot, we also got, I think, a pretty good understanding of what do these knowledge graph embedding methods actually learn. So what are they actually good for, and what are they not good for, right? And what's missing? So one of the things that really I think is a good take-home message is that when you learn these embedding methods, what you essentially do is you learn a very fine-grained typing, like a latent type for the entities and the relations, right? So for instance, this is maybe a good way to think about it. It's like a clustering almost, right? So for instance, here you might have all the cities. Maybe here you have all the cities in North America, and here you have all the cities in Europe, let's say, right? So you get kind of a latent, you learn automatically a latent type. So not the type in the sense of, car, actor, but it's a latent type that's oftentimes, I think, a conjunction of types that, you guys, when you work, for instance, with description logic or something like this, actually talk about. And that's good, right? If that's all you have, that's still better than nothing. But what do then methods not really learn is something like a truly relational model. So for instance, it might be that if someone is married to a particular person, you know that something is true about that person. To capture this type of information in an embedding method is very, very difficult, because what you end up doing is your latent type or your latent typing of entities is getting too fine-grained. And then you actually don't do well anymore, and you don't generalize well anymore, right? But still, right, if you have that knowledge, it's like if you, for instance, have a rule that tells you if that person is married to Barack Obama, then she's the first lady or something like this, you should still use it, right? And the big question is, how do you do that? So how do you combine these types of embedding methods that essentially learn these latent types with relational models? And that's something that we are also working on. Then I also mentioned that, and this was first observed by Tutanova, that for some knowledge graphs, so there was a lot of research using these scoring functions and getting decent results. But then actually someone sat down and asked, so can we actually, so what would we actually, what is actually the result if we use very simple relational features? And what I mean by very simple relational features is something like, for every entity, is there an outgoing relation that says located in, right? If it's there, its feature value is 1. If it's not there, feature value is 0, right? So these kinds of very simple relational features, it turns out that for many of these benchmark data sets that or for some of them at least, that I mentioned to you before, you get actually very, very good results with these very simple relational baselines. So you can oftentimes actually outperform embedding methods. And this holds true mostly what I would call dense knowledge graphs, where you have lots of connections between the entities. Then oftentimes the relational model works quite well. If the knowledge graph is very sparse, these types of embedding methods usually work better. So this is kind of our, let's say, anecdotal experience here, right? So that's kind of, yeah. Also, one thing I should mention is if you have a very sparse knowledge graph and you're using a relational method, so a rule-based method, you know, the quality of your predictions depend a lot on the quality of your rules. And the problem there is that if you don't have a rule that tells you something about the particular query that you're asking, your answer is completely random, right? And this is, I think, also where when you combine a relational model that works really well if one of its rules is actually applicable, with a method that if there is such a rule is actually missing, and the answer would be random for a logic-based relational model, then you can fall back to the embedding model that kind of learns these latent types. That's a very good actually combination that oftentimes works better. And this is exactly also what Alberto is going to talk about. I also briefly wanted to mention that, you know, this kind of looking at a knowledge graph as a tensor, there are also some alternative ideas here, and people have used, for instance, in the context of information extraction. So this is something also from Sebastian. It's a slightly different representation where you essentially just have pairs of entities sitting on the sides here. And then the rows are essentially indicating for every relationship if that relationship is true for that pair. And then what you can do here is you can also compute the matrix factorization. So that's what Sebastian has termed universal schema. And actually we have also, and I will talk about this a bit later, used exactly the same type of representation here to learn rules from it and then to use these rules for things like knowledge-based completion. Okay, so this is kind of the first part of the lecture that kind of, it intends to give you kind of a very quick introduction to embedding methods for knowledge-based completion for multi-relational graphs. And now the second part of the lecture is going to talk about learning from local graph structures. And I wanted to use that break in a sense also to maybe ask you if you have any questions so far, or if things are, I'm happy to take questions at this point before I move on. Yes. Yes, that's a very good question. So I'm repeating the question for everyone. The question was, I mentioned, embedding method works pretty well when the graph is dense and not so well when it's sparse. So how do you determine in what situation you're actually in? That's a very good question, and I think there is no, theoretically solid answer here. I think at the moment we're at the stage where we just have to try. And again, this is what Alberto is going to talk about. If we actually combine relational methods, like using rules somehow, and I will talk briefly also about this, and using these embedding methods, then you're kind of on the safe side, right? Hopefully. But it's a good question. It's vague. There is no formal definition of what's sparse and what's not sparse. Yes. Yep. Yeah, so this is a very good question. Also because I think many of you are coming from the from this background of we have an ontology, some sort of schema. So this is also kind of the people who work on this type of who approach knowledge-based completion with embedding methods are how should I put it? They don't care so much about the distinction, right? You should distinguish between what's what's your so to say your C box and what's your A box, so to say, right? But there they don't do it. So if you have something like a subclass relationship, you model that as an edge. If you have located in, you model that as an edge, right? If you have even something like a property like male or female or whatever, it's usually modeled as a node, and then you have an edge from Arnold Schwarzenegger to male. So everything there is kind of assumed to be just an edge, right? Flat. I think the idea to distinguish between what's in your what's in your schema and what's not in your schema is actually an interesting problem to also incorporate maybe here. But so that's a good question. But people who work on this are very kind of machine learning. They're very kind of they don't want to be bothered with these fine distinctions. That's my feeling. Okay, thanks for the question. Any more questions, or should I move on? Okay. So as I said, the first part was about the perspective of learning from knowledge graphs as the perspective of learning from or representing, decomposing higher dimensional matrices, tensors. And I think another perspective is that is very helpful in understanding what people are currently doing specifically in also the representation learning community is learning from local graph structures. I wanted to mention right away, just because we are learning from local graph structures doesn't mean that we cannot capture emerging global properties of a graph, right? So because what oftentimes happens is that we kind of recursively propagate, and you will understand what that means later, representations between the nodes in the graph. And eventually, you can also move to very far places, in a sense. Starting from one node in the graph, you can actually move to very far places in the graph. So it's not really that the features that you learn here are purely local. But you start, in a sense, with these kind of local structures, and you're trying to learn something from these local structures, and then hierarchically build more meaningful, more global features. I think there's also a pretty good way to distinguish here between two different types of local structures that people very often use. One is paths or random walks in graphs or in knowledge graphs. And the other one is local neighborhoods, right? And I will cover both of those and also talk a bit more about what people have done there. So let's start with learning from random walks and paths. So the basic idea here is that we mine frequent paths. So we have a knowledge graph. We start many random walks from different nodes. We walk around randomly, right? A random walk is just, okay, if I have 3 neighbors, I go to each of those neighbors with probability 1/3, right? That's a random walk. And I walk around in the graph a lot, and then I look, okay, what are the frequently occurring types of paths that I actually encounter when I do that, right? And then I use those somehow as features in some sort of machine learning model. So that's a very common and recurring theme. So again, in a multi-relational graph, this just means, you kind of walk around in it. You notice maybe, oh wow, so these are the walks, but you might notice I have a lot of paths that have something like A located in B, B capital of C. It happens a lot in my graph, or let's say more than 10 times or something like this. So I want to actually use that as a feature, right? So that's kind of at the core of these ideas. In graphs where you don't have many relations, so in single relational graphs, so for instance a social network, right? You can also do this. And then this is actually relating back to what Sebastian Riedl was talking about earlier. What you can now do is you can essentially extract all of these paths that you got during your random walks, and you can treat them as a bag of nodes, right? So earlier, Sebastian explained how every sentence or phrase in a document can also be represented as a bag of words. And then there are these methods like word2vec, which I'm sure most of you have heard about, which essentially then allow you to learn these latent representations for the words, which again, Sebastian has mentioned quite a bit before. And the same thing you can do here. You just walk around in the graph, you record these particular paths that you encounter, and then you just treat the nodes that you encountered as the words. And then you apply some sort of, word2vec type objective. In this particular case, it's the continuous bag of words. You have a linear embedding for your entities in the graph. You do some sort of averaging, and then from that averaging, you want to predict essentially the context node, right? So you want to be able to predict from this particular node here and that particular node and its representation and the mean of those representations. You want to be able to predict Tokyo as a context. So Tokyo should have a high probability there. Very, very similar to the word2vec type objectives. Okay? And in the end, you get a node embedding, and you can use it for something like node classification or link prediction. And this is what started also the trend of kind of deep work has started the trend of using paths in representation learning. It's a paper from 2014. The idea is, again, you have random walks, you build representations. So every node in your graph is associated with a vector. And then you apply some sort of loss to actually learn these embeddings in a completely unsupervised way in this case. Okay, so that's kind of the representation learning way of learning from paths. The other one that is kind of, I would say, seminal in its impact on the field is, it's called the path ranking algorithm. The idea here is that, okay, you now do random walks in a multi-relational graph. And again, you kind of keep track of the types of paths that you encounter quite a bit, right? So you might have some sort of threshold on how many times you want to see a path before you use it as a feature. And then you just train a very simple logistic regression classifier, right? So for instance, if, let me check if I have an example there. Yeah, sorry. So if you, for instance, want to know, okay, where is Hawaii located in, right? And you have seen a lot the feature, the path has capital located in. Then you use that as a feature in your model. And when you now train the model, you realize, oh, this is a good feature for predicting located in, right? Because whenever I have A has capital B and B located in C, then A also located in C, right? So this feature tells you something about the located relationship. And you just use it in a very simple logistic regression model to predict essentially these links. And this is what's called path ranking. This is actually an algorithm that's introduced by yet another speaker that you will have in ILP, William Cohen, and his students. Okay, there are also other types of methods for mining path-like features. So for instance, I worked on a method to mine essentially schemas from knowledge graphs, where the idea is we do this kind of representation. Back then it wasn't called universal schema, but kind of the same idea. You have pairs sitting on the rows and relations sitting on the columns. And then you actually apply association rule mining. And what you end up getting are rules of this form here, right? So you can also get this you can learn range restrictions, you can learn subsumption, these kinds of things, by just building this particular matrix and applying association rule mining on it. The problem with this approach is that you're very much restricted to learning rules where you always have AB, right, in the relations, because that's always what you have on the left side here. And there's a very nice generalization of this idea. It's called AMI. It comes out of the Max Planck Institute. And this is essentially very nice and really recommended if you want to also mine logical rules, horn rules from knowledge graphs. You just essentially apply it to your knowledge graph of choice. And it returns, you can also provide some sort of thresholds that have to be reached before the rule is returned. And then it returns all of the closed horn rules that are satisfying all of these thresholds. Closed means all variables appear at least in two relations. Okay, so something like this rule here would be found by the method. No, there's no negation though. It's just classic non-negated horn rules. And this is really nice because it's also highly optimized. You can see, you know, even for pretty large knowledge graphs, you get in not such a big amount of time, you get all of these rules. And it's actually really cool to just try this on something like Freebase, for instance, and see what type of rules does it actually find. Again, the input is a knowledge graph, output is a bunch of rules. And then the big question is, right, so what can we do now with these rules? We want to use them somehow in a meaningful way. And that's one of the questions that I think is super important and interesting. So how can we combine these rules that we know about now with something like an embedding method that I mentioned in the first part of my talk? And one of the ways to do this is, just very briefly, for instance, to extend the idea of trans E, right? I told you trans E was given a triple. You essentially have your objective that the embedding of the head entity plus, so translated by, the embedding of the relation entity should lead you to the embedding of the tail entity, right? This was the previous trans E objective. And now you can actually generalize this to paths. So if you, for instance, know that this is if this is actually true, right, in the knowledge graph a lot, you can incorporate that also in the objective. So you actually have now two translations, right? One per relation type. One way to do this. Another way to do this is by Pasquale, actually, and also Sebastian Riedel. The idea here is that if you have knowledge of certain rules that you know to be true, because, for instance, you mined them from the knowledge graph, let's say this particular rule here, and you now have some sort of embedding method that scores you triples, right? And you see that the embedding method is off because it scores, for instance, the antecedents high and the consequence low. Then you can use that in some form of loss and backpropagate so that hopefully this score here gets higher, right? So you can use essentially known rules as what they call adversarial examples. So examples that are currently not really satisfied in the numerical part of in the embedding space, so to say, right, of the model. So that's another way, which is orthogonal to the way that by encoding paths. And Alberto will talk about the way that kind of we came up with, but more later. Okay, so this was kind of an overview of learning from local structures, learning from paths, and now we are turning to learning from local neighborhoods, which is a bit different, right? So again, before it was a path is kind of connecting two nodes in the graph, or is usually found by performing random walks or by running something like AMI. But now you can also think about actually, can we, if we are interested, for instance, about something is there a link between two entities, for instance, we could actually extract the neighborhood of those two entities or of many other pairs of entities and then learn something from that. So the motivation for doing this, and I mentioned this already briefly before, is grounded in the observation that good representation learning is usually composed bottom-up, right? So for instance, in computer vision, what you do is you look at very, very small receptive fields, so squares that you move over the image, and they're just 3 × 3 pixels, right? But you hierarchically compose those features so that in the end you get a very good feature extractor for an entire image. And so the question, and this is also what motivates our work, is in logic, is there a suitable notion of locality, right? Because especially also in knowledge graphs, it's a highly irregular domain, as I mentioned before. It's not so easy as just saying, okay, we take a square grid and we move it over the graph, right? That concept doesn't match. So the question is, what do we do there? And actually, there is a nice a nice theory actually in finite model theory, named after Geifman, who is a famous finite model theoretician. And it's a nice little result that also motivated some of our work. Namely that a Geifman graph, so given a knowledge graph, you can build a Geifman graph, and the Geifman graph is very simple. It's actually just, there is an edge between two nodes if they participate in one of the relations, one of the predicates, right, in your data. And then you can look at the R neighborhood. R neighborhood here just means, given a node or a pair of nodes, you go R hops, up to R hops away from that node. And there's a very interesting result in finite model theory that states that, which is called Geifman's locality theorem, which states that every first order sentence can be written as a Boolean combination of these local sentences, which shows you that there is also, at least in a vague connection here, there is also some sort of notion of locality, at least in first order logic. So that should allow you to go from more local feature types, or more local characterizations of your input, to more global features. And so the goal so this is one of the things that we actually did, was to understand, okay, can we now actually sample our neighborhoods from knowledge graphs, then actually have a particular query that we want to answer, and then train a model on these many local neighborhoods that we extract in the graph to actually predict whether the query is false or true. And the idea is very simple. So you sample a lot of local neighborhoods. So for instance, for every pair that you have 444 in your knowledge graph, you sample the neighborhood. You evaluate what we call relational features. So these can be path features. This can come from AMI, for instance. And then we evaluate whether these features are true, and we can even count, like, if we have some sort of, if we have free variables, we can even kind of interpret that as a counting query, right? How many of these features are actually true in the neighborhood, not just is it true or false. And this kind of gives you a feature vector for all of these neighborhoods, right? And then you can train a very simple machine learning model based on these neighborhood representations that are now vectors to actually make a prediction. And what you do is very simple. You have a target query, something like what is Tokyo a capital of? What country? You now sample a number of R neighborhoods of pairs, of which you know that this is true in your knowledge graph as positive training triples. You also do some sort of corruption, like I mentioned before. You might just corrupt entities by sampling a random one. Then you evaluate the relational features to get your vector, and then you train the model. It's very simple, actually, right? It's, and also very similar to other methods. And then at inference time, you do the same, right? You just, if you want to know, is there a particular link or relationship between these two entities, you extract the neighborhood, you apply the pre-trained model, and it gives you an answer of yes or no. Right? And the nice thing here is also that this remains interpretable in the sense that you can inspect the model and you can see which of the rules actually was triggered to make the prediction. So it's kind of, there is still the connection to the logical form. And of course, still this is trained end to end. But I shouldn't go too much into this. It's just to show you this is a loss function that we can define. We can apply, standard gradient descent, these kinds of things. Okay, now I also want to talk a bit about some recent advances in learning from local graph structures where we have single relational graphs, because I think there's also a lot of potential to apply these ideas to multi-relational graphs. So maybe also as an idea for future research. I mentioned this before a couple of times, right? When we have regular graphs, so for instance, you can kind of interpret an image like a grid graph, right? And that's called the regular graph because every node has the same kind of neighborhood structure. If you have a regular graph, doing something like, applying something like a convolutional neural network is very straightforward, right? You just kind of move this, receptive field that I have mentioned before, from left to right and from top to bottom, and you can then learn something from it. Now, what do you do when you have these types of irregular graphs, right? Where the neighborhood structure for all of the nodes looks very, very different. And this is kind of the area that's called graph convolutional networks. So it's kind of concerned with the question, okay, given that we have such irregular neighborhood structures in most real-world graphs, how can we actually apply ideas similar to what is used in convolutional neural networks on images or on text? And the most important feature, I think, of convolutional networks is actually I would say, the weight sharing property, right? When you move a receptive field over your image, you are using the same set of parameters no matter where in the image you are. And the same kind of thing you want to also be able to do for graph structure data. But the big question is, in order to do actually weight sharing, you need to kind of end up with a fixed size representation for your neighborhood. So you have a node, you get some sort of neighborhood for the node, let's say the 1 or 2 hop neighborhood. And you now want to kind of aggregate the features. So what you see here, these colorful bars, are the features that are sitting on the nodes. You want to aggregate them into a fixed size representation, because then downstream you can then apply, other types of linear transformations with the same type of parameters, and so then you apply these parameters to all the different parts of the graph. But again, the big question is, how do you do that? So how do you actually get from these highly irregular neighborhoods to fixed sized vector representations? And there are different, I always like to think of what's out there at the moment and what people are working on as kind of a spectrum between two different methods. One is a method that kind of very straightforwardly tries to emulate, convolutional networks on graphs. Again, the idea is, okay, here it's easy. We have the same neighborhood structure for all of the nodes. We kind of learn these hierarchical features. Things are easy because it's a grid graph. But what do we do when we actually have these irregular shapes? And one of the ideas is to actually do what's called a neighborhood normalization. So, right, because if you want to aggregate the features of your neighborhoods, and the neighborhood can be of many different sizes, you might want to actually kind of you need to kind of condense that down to a fixed size. And so one of the things that you can do is you can what's called normalize the subgraph. So normalizing actually means we assign a ranking to the nodes by for instance, the distance to the original node, which is here colored in red. We can apply something like graph labeling methods, like for instance centrality measures or Weisweiler-Lehmann. These are methods that essentially kind of reflect how well connected the node is to the node that you started with, the red node here in this particular case, right? So you can think of it as kind of ranking the nodes according to how closely connected they are to the root node. And when you do this particular ranking, you can then in the end, if you have, for instance, too many nodes, and I just want to have exactly, let's say 9 or a size 9 input for my neural network, you can also essentially just cut or remove certain nodes based on that ranking. So that's one idea. One of the advantages of this idea, yes. This one here? Yeah. No, sorry. So this enumeration. I just tried to make a link between. Yes. So this enumeration here is essentially because you do it. So this the green ones are the 1-hop neighborhood, right? The beige ones are 2-hop neighborhood, and so you know that all of the elements in the 1-hop neighborhood will be ranked higher because they're closer, right? But then you might still end up with, like here for instance, right? You might still end up in the 1-hop neighborhood with 2 nodes that have the same type of number here. But then you can use something like, for instance, something like Weisweiler-Lehmann, a measure that essentially takes into account the connectivity to other nodes. So how well connected is this node? and then you rank this particular one higher because it is actually connected to 4 other nodes as opposed to only 3. And so this is a way to break essentially ties. And in the end, you might still end up with ties, and those you can actually break with a canonicalization algorithm on graphs. And this is something we actually did. So because if you have very small neighborhoods, applying this is linear time, very fast. So you can also break ties here. And then if you actually train on top of that, right? Now you have these kind of normalized neighborhoods. If you train now a vanilla convolutional neural network on top of that, you can actually also see the types of features that the model is learning. So that's kind of an advantage, I think, of this method. So for instance, for some sort of preferential attachment graph, small world type graph, you learn a different set of features. These are just examples, right? Of how these little features of neighborhoods look like that you learn. Then let's say for a random graph. So this one here is a random graph. And this relates to the kind of the graph kernel work that you also heard about before, right, from Paolo. In a sense, you can think of this as kind of automatically learning graphlet kernels for graphs. So that's kind of one possible idea. On the other end of the spectrum is what was termed graph convolutional networks. And the idea is kind of the opposite. So actually, you can imagine when you do the type of normalization that I just talked about, you get also very kind of different types of structures, right? Because you kind of always keep the top, let's say, 10 ranked nodes, and they might look very different, depending on which neighborhood you're looking at. So there's a high variance in what you actually see when you train, and this might be bad. And so, kind of, the idea that's on the exact opposite is to actually just take the features that you have sitting on the nodes in your neighborhood and just do some sort of mean pooling, right? Again, the goal here is, right, this is again to take a step back. The goal is to get from heterogeneous neighborhoods and the features that are sitting on the nodes to a fixed size vector representation. And one way of doing this is to just look at the neighborhood and just mean pool, essentially. Like this is the core idea here, to mean pool the vectors into one vector that is then downstream fed into other types of parts of the model, the learning model. And that's what's called graph convolutional networks. And that's also has been used very, very successfully for many different tasks. So for instance, also specifically semi-supervised learning. Again, this is from Thomas Kipf. This is kind of one of the illustrations that he likes to use. The idea is really kind of you have a particular type of average pooling from your neighborhood, you apply a nonlinearity, you pool again, and so forth, right? So intuitively speaking, that's what's happening here. And so now also on this type of spectrum here, you have a lot of different types of methods. And again, the difficult part is really getting from this kind of heterogeneous neighborhoods to a fixed size vector representation. I'm going to quickly mention this. This is also some work. So these types of graph neural networks that are now used quite a bit are also very good with missing data. But I won't go any further into this. It's called embedding propagation. It's a method that works with unsupervised, multimodal, and missing data. Then there was also a recent proposal to use attention. So you heard about attention earlier today from Sebastian and Pasquale. And you can also apply ideas that are similar to these ideas that were mentioned this morning to graphs. The core idea is to essentially just say, okay, we take essentially attention, we have essentially attention weights, and we take some sort of combination of the vectors that are on the neighborhood nodes with these attention vectors, and then use this to compute a weighted average, right? So before we had this kind of pooling that I mentioned, it's kind of like similar to mean pooling. And here you can now learn, in a sense, for every node, how you combine essentially the embeddings of the neighborhoods. So it's kind of an extended version of pooling. Okay, just I mentioned this. This was going a bit. It was going slightly away from multi-relational graphs because these things are the last couple of things I mentioned are mostly applied to single relational graphs. But I also think that there is a lot, as I mentioned before, a lot of potential to also extend those methods to multi-relational graphs. Okay, so I have about 15 minutes left. And I have about 3 slides where I want to go through some kind of experiences that we made, some observations we made by kind of working with these types of things. But is there at the moment a question that you want to ask? Otherwise, I just continue. Okay. So let's go to the last part. As I mentioned before, kind of also to summarize kind of some of the insights, right, of the lecture so far. I hope insights. Is that embedding methods learn these latent type representations. So they can be, I think, very helpful as fallback methods when the relational features, the logic-based features are brittle and don't really capture a particular situation, cannot be used in a particular situation. There's also this dichotomy of logic rule-based features. Either they work perfectly, right, because they get a grip on the type of question that you want to ask and you can infer something, or they completely fail. And then in the worst case, your answer is just completely random. You don't know. Relational features tend to outperform embedding methods on dense relational structures. So again, I think it's a mistake to say, let's just all work on embedding methods, because I think rule-based methods sure perform really well in many situations and shouldn't be ignored. But the embedding methods, again, are very good at kind of like a fallback in sparsely connected knowledge graphs, and they work better there than, let's say, rule-based methods. If you mine the rules and then apply them in some way. And again, I mentioned this also before, the motivation for the second part of the lecture by Alberto is now how can we actually combine embedding type features and relational rule-based features. And also how can we even combine these things with, let's say, for instance, also other types of features like numerical features, right? So many of these knowledge graphs have geolocations, for instance, sitting on the nodes, or you have birth years or whatever. Can we also incorporate these types of things into the learning process? We have, and this is also maybe going back a bit to us being an industry lab. So knowledge graph embedding methods, despite also my my criticism that I hope I kind of conveyed sufficiently to just believe that they are great and you should use them. It's not the case. You can still actually use them quite a bit, and especially in conjunction with rule-based approaches. And so we have successfully used knowledge graph embedding methods in conjunction also with rule-based methods, something that Alberto will talk about, for product recommendation, for instance, polypharmacy predictions, patient outcome prediction, and drug discovery type problems. And you get really good results there, actually. And you can use that really also for practications. And this is maybe something that I haven't mentioned yet. One of the big problems with rule-based methods and also the type of stuff that you heard about earlier in the school, like Markov logic, problog, these kinds of things, they're very expensive, right? So, I mean, I have made experiences where we wanted to apply something like Markov logic, and it just didn't scale well, even though we really wanted to, and in many cases it is useful and makes sense to do that. It just oftentimes doesn't scale. And that's one of the big advantages of that stuff here, right? In many cases, this is something you can quickly try. You can train it with gradient descent. It takes a couple of hours in the worst case, and you can do predictions very efficiently. So that's really one of the advantages of these methods. And there's also maybe something to keep in mind. I'm not saying, we should not forget about all the stuff that's expensive, that's, NP hard, but it's also something to keep in mind. You know, especially in industry, you need also scalable methods that actually get you something quickly. Another observation is that simple methods tend to be more robust, meaning they generalize better in several application domains. So when you look at, right, so what happens a lot in machine learning, you all know this probably, is that people overfit on certain benchmark data sets, right? So you have a benchmark data set like Freebase, and every year, 100 new papers are coming out that are a little better than the previous ones. But in the end, there is at some point a ceiling, right? You're just maybe getting better by chance, or because you have maybe a better hyperparameter here or there. And then oftentimes it's eye-opening if you actually then build a new benchmark data set and apply all of these methods, or some of them. Oftentimes what you find is that the simple ones actually on average perform the best. So something like DiskMold or TransE, this is our experience, are usually working really well out of the box if you have a completely new knowledge graph. And the ones that are more complex are usually more difficult to tune again, and they usually don't generalize well. Including more modalities, and again, I'm referring to Alberto's part of the lecture, improves the results. So for instance, we have results with numerical features and images where the results are getting better. But the improvement over simple methods is modest in many cases. So also to keep the expectation, you know, at a certain level. I mean, they're better and they work better in many ways, and it's good to use them. But also, you know, again, I want to kind of make a case here for simple, when it comes to embedding methods, simple methods. It's extremely important, and this is maybe also interesting for you guys. In industry, it's also very important to be able to understand why a prediction was made. So when you just train an embedding method, and the embedding method tells you, yeah, this triple is true because it has a really high score, you have to believe me. This is oftentimes something that you cannot actually use in industry. So that's also one motivation of combining these types of embedding methods with methods that still allow you to look at the rules that actually contributed to the prediction that you made. So that you can inspect the rules and then actually do further research and further look into the prediction to understand what's actually going on. Extremely important in the biomedical domain, in the medical domain. So that's also a big argument, a very big motivation for combining these two methods. And also, just also a motivation for, you know, in general, statistical relational learning as a research area. There's a lot of hype about, you know, computer vision, speech, you know, machine translation, these kinds of things. But actually, when you look at what is actually, what most of the companies, what do they actually have in terms of data, it is in, I would say, a high percentage, 90% relational data. So they have a relational database system, they store all kinds of stuff there, they want to make sense out of it. And so relational learning, statistical relational learning is a very, very good kind of also, you know, knowledge to have. Also if you want to work in industry. Because actually when you think about how many businesses actually work with images, it's a very small number, right? Most businesses work with relational data. So also just to kind of end my part with, you know, what you guys are working on is very meaningful and also sought after in industry. Okay, that's it. Thank you very much.